Welcome to Learning with UNP. In this session of Data Science and Mastering Machine Learning, we are going to understand about k-means clustering, practical implementation on a project. In here, we are going to use k-means clustering to solve a problem. The objective is to use the k-means clustering algorithm on the red wine quality dataset to find natural groupings of wines based on their chemical properties. This will help us understand which wines have similar chemical characteristics. Let me give you an overview of what exactly we will be doing in this project. In this project, we will implement the machine learning process using Python. We will load and explore a wine quality dataset, split it into training and test sets, applying the k-means algorithm and determining the optimal number of clusters, and finally evaluate the model's performance with appropriate metrics. We will use pandas, numpy, scikit-learn, and matplotlib for this task. Let's begin with understanding the dataset. The dataset name is Red Wine Quality Dataset. The red wine quality dataset contains information on various chemical properties of red wines. The attributes in the dataset are fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, sulfate, alcohol. The quality. To begin our project, the first step is to load the dataset into our Python environment. We will use the pandas library, which is widely used for data manipulation and analysis in Python. Below are the elaborated steps and code to load the dataset. First, we will import NumPy and pandas. Then, we will load the dataset from an CSV file into a pandas data frame. Finally, we will inspect the first few rows to understand the data structure and content. Here is how we import various libraries. NumPy as NP for numerical operations, pandas as PD for data manipulation and analysis, Seaborn as SNS for statistical data visualization, matplotlib to display plots in line in Jupyter notebooks. Now we will load the wine quality dataset into a pandas data frame using the read_csv function specifying the file path. This allows us to easily manipulate and analyze the data. In here, data.shape gives the number of rows and columns in the dataset data. This output indicates our dataset comprises 1599 rows, instances, and 12 columns attributes. These attributes include various chemical properties along with a target variable quality, indicating quality rating. Undertaking the shape provides a quick overview of the dataset size and structure, crucial for data exploration and modeling. Before using the K-means algorithm, you may need to pre-process your data if required. This can include cleaning the data, handling missing values, and encoding categorical variables. This line of code checks for missing values in each column of the data frame and sums them up. In this dataset, there are no missing values in any of the columns as indicated by the output of zeros for each attribute. After checking carefully, we found no missing values in our dataset, meaning all entries have all the necessary information. Also, all the data is in numbers already, so we don't need to change anything about how it is stored. This allows us to proceed directly with applying the k-means algorithm without needing to handle any missing data, thereby simplifying our pre-processing steps. Now, let's move on to the next step of understanding normalize method. When using distance-based algorithms like k-means clustering, it is important to normalize the data. If we don't normalize, the variables with different scales will affect the distance calculations unevenly, leading to biased results. We import the pre-processing module from sklearn library because it offers functions to prepare the data for machine learning models. This includes scaling features, standardizing data, encoding categorical variables, and more. Importing this module allows us to properly pre-process our data before using it in the models. Now, use the normalize function from scikit-learn's pre-processing module to normalize data matrix. Normalization scales each data point so that it has a unit norm. Norm is a measure of its length, which is done by dividing each data point by its Euclidean norm, L2 norm. This ensures all features are on the same scale, which is important for machine learning algorithms that are sensitive to the scale of the data. After normalizing the data using preprocessing.normalize of data, you should reassign the column names. Normalization can change how the data is structured or represented. By specifying column names, you make sure each feature keeps its original name. This is important for clarity and consistency when analyzing or visualizing the data, as it ensures that columns are correctly labeled and aligned with their respective names. Now let's look at the normalized data. By passing data and column is equal to column names to pd.data frame, you create a data frame where each column has normalized values but keeps the original feature names. This makes it easier to manipulate, analyze, and visualize the data using pandas and other Python tools. Next, we will apply our approach to normalize data. First, we'll visualize the features to understand the data better. Then, we will build the k-means models with 3 clusters and 2 clusters. After that, we will evaluate each model using appropriate metrics to see how well they group the data based on its patterns and characteristics. Here comes visualizing the features. The Seaborn library SNS helps create a scatter plot to show how two variables from the dataset relate to each other. Before we use K-means clustering algorithm, let's look at how wine samples are distributed based on their chlorides and pH values. Similarly, let's examine how wine samples are distributed based on their free sulfur dioxide and total sulfur dioxide, and also density and quality values. Here comes the model building. We begin by importing the k-means module from scikit-learn.cluster, which is essential for implementing the k-means clustering algorithm. This module allows us to create k-means models, fit them to our dataset to identify clusters, predict cluster assignments for new data points, and evaluate the cluster's effectiveness using relevant metrics. This import is crucial for building and analyzing k-means clustering models in our project. We will now look at first model with 3 clusters. We set up k-means clustering algorithm with specific parameters. Here is what each parameter signifies. N clusters is equal to 3. It specifies that we want to identify 3 clusters in the dataset. This parameter determines the number of clusters the algorithm will attempt to find. Random set is equal to 42. It sets the random seed to 42 for reproducibility, ensuring that results are consistent across different runs. N init is equal to auto. It automatically determines the number of times the algorithm will run with different centroid seeds. This parameter controls the number of initializations to improve the quality of the final clustering. This setup prepares the k-means model to partition the dataset into 3 distinct clusters based on the data's features. The k-means model selects features from the dataset and applies the model to them. The fit-predict method fits the model to the data and predicts which cluster each data point belongs to. The resulting cluster variables stores these cluster labels indicating the group each data point falls into. Now, we assign the cluster labels stored in the cluster variables to a new column named cluster in the data frame data. Each row in the data frame now has a corresponding cluster label indicating which group or cluster that particular data point belongs to. K-means cluster centers returns the coordinates of the centroids, which are centers of the clusters identified by the K-means algorithm. Each centroid is represented by a point in the same dimensional space as the input data, where the number of dimensions corresponds to the number of features used in the clustering. These centroids represent the average position of all data points assigned to their respective clusters, serving as representative points for each cluster's characteristics. This visualization shows how the K-means algorithm has partitioned the wine samples into distinct groups based on their acidity levels, highlighting the central points, which are centroids of each cluster. This helps us understand the main characteristics of each group. We visualize the clusters identified by the K-means algorithm based on the chlorides and pH features of the wine dataset. We visualize the clusters identified by the K-means algorithm based on the free sulfur dioxide and total sulfur dioxide features of the wine dataset. Let me explain you one chart here. As you can see on the screen, we can see 3 different clusters with the colors yellow, red and blue. After applying K-means clustering model, the data points are made into clusters, wherein each cluster represents the data points that are similar to each other and are different from other clusters. The black points in the middle of the cluster represents the center of that particular cluster, known as centroid. As per the centroids, the clusters are made accordingly. The same happens with other charts too. We visualize the clusters identified by the K-means algorithm based on the density and quality features of the wine dataset. Now, let's look at the evaluation metric. There are various evaluation metrics available to evaluate the performance and effectiveness of the k-means clustering algorithm. We print the inertia value of a k-means clustering model which measures how compact the clusters are. Inertia is the sum of square distances from each sample to its nearest cluster center. Lower inertia means clusters are tighter and better defined. This metric helps evaluate how well the K-means algorithm has grouped the data based on the current cluster centers. First comes Silhouette score. The Silhouette score ranges from -1 to +1. A score close to 1 indicates that the points are well clustered and far from other clusters. A score close to -1 indicates that the points might be in wrong clusters. The Silhouette score of 0.82 is relatively high, indicating strong separation and compactness of clusters. This suggests that the clusters are well defined and distinct from each other. Second comes Davis-Boolean score. The Davis-Boolean score measures the average similarity ratio of each cluster with its most similar cluster. It ranges from 0 to infinity, with lower values indicating better clustering. The Davis-Boolean score of 0.27 is low, indicating very good cluster distinctiveness with minimal overlap or similarity between clusters. Third comes Kalinsky-Harabaugh score. The Kalinsky-Harabaugh score or variance ratio criteria is a way to see how well your data points are grouped into clusters. It looks at two things within cluster dispersion, how close the data points are to each other within the same cluster, and between cluster dispersion, how far apart the clusters are from each other. A higher Kalinsky-Harabaugh score means that the data points within each cluster are very close to each other and the clusters themselves are far apart, indicating well-defined clusters. A Kalinsky-Harabaugh score of 2209.86 is very high, indicating that the clusters are highly compact and well separated. This suggests excellent clustering performance. These scores show that the clustering model is excellent at grouping the data into distinct and well separated clusters. The high Celote and Kalinsky-Harabaugh scores combined with low Davis-Boolean score demonstrate the model's effectiveness in creating clear and separate clusters. Now we will look at second model with two clusters. In here, we will implement the k-means algorithm with a specific configuration of two clusters aiming to partition the dataset into distinct groups based on their features. We again set up the k-means clustering algorithm with specific parameters. Here is what each parameter signifies. N clusters is equal to 2. It specifies that we want to identify two clusters in the dataset. This parameter determines the number of clusters the algorithm will attempt to find. Random set is equal to 42. As mentioned above, it sets the random seed to 42 for reproducibility, ensuring that results are consistent across different runs. N init is equal to auto. It automatically determines the number of times the algorithm will run with different centroid seeds. This parameter controls the number of initializations to improve the quality of the final clustering. This setup prepares the k-means model to partition the dataset into two distinct clusters based on the data's features. The k-means model selects features from the dataset and applies the model to them. The fit predict method fits the model to the data and predicts which cluster each data point belongs to. The resultant cluster variables store as cluster labels indicating the group each data point falls into. We assign the cluster labels from the cluster variables to a new cluster column in the data frame data so that each row now shows its cluster. The k-means cluster centers gives the coordinates of the cluster centers representing the average position of points in each cluster and showing the typical characteristics of the clusters. This visualization shows how the k-means algorithm has grouped the wine samples based on their acidity levels, highlighting the center points, means centroids, of each cluster. It helps us understand the typical characteristics of each group. Over here, let me again explain you one chart. As you can see on the screen, we can see two different clusters with the colors red and blue. After applying the k-means clustering model, the data points are made into clusters wherein each cluster represents the data points that are similar to each other and are different from other clusters. The black point in the middle of the cluster represents the centroid of that particular cluster. As per the centroids, the clusters are made accordingly. The same happens with other charts too. We visualize the clusters identified by the K-means algorithm based on the chlorides and pH features of the wine dataset, the free sulfur dioxide and the total sulfur dioxide features of the wine dataset, the density and quality features of the wine dataset. Now let's look at the evaluation metric. We print the inertia value of a K-means clustering model which measures how compact the clusters are. Low inertia means clusters are tighter and better defined. This metric helps evaluate how well the K-means algorithm has grouped the data based on the current cluster centers. First comes Silhouette score. The Silhouette score of 0.79 is quite high, indicating strong separation and compactness of clusters. It suggests that the clusters are well defined and distinct from each other. Second comes Davis-Boolean score. The Davis-Boolean score of 0.32 is relatively low, indicating good cluster distinctiveness with minimal overlap and similarity between clusters. Third comes Kalinsky-Harawa score. The Kalinsky-Harawa score of this mentioned here is high, indicating that the clusters are compact and well separated. This suggests that clustering performance is good. These scores show that the clustering model is excellent at grouping the data into distinct and well separated clusters. The high Silhouette and Kalinsky-Harawa scores combined with the low Davis-Boolean score demonstrate the model's effectiveness in creating clear and separate clusters. Finally, to determine which clustering model is the best, we typically look at highest values for Silhouette score and Kalinsky-Harawa score and the lowest values for Davis-Boolean score. The K-means model with three clusters evaluated on normalized data is the best clustering model based on the metrics. It has the highest Silhouette score of 0.8173, indicating strong cluster separation. The lowest Davis-Boolean score, 0.2747, showing good cluster distinctiveness, and the highest Kalinsky-Harawa score of 22209.8574, reflecting well-separated compact clusters. This is all about today's lecture. See you in the next lecture. Thank you.